Our topic is transformer on load. In last topic we have discussed about the transformer on no load. In this topic, when the secondary of the transformer is completed through an external load, then the transformer is said to be loaded and the current starts flowing in the secondary of the transformer. Now this secondary current I2, we denote the secondary current by I2, will be in phase or will lag or will lead with respect to secondary terminal voltage V2 if the load is non-inductive, inductive and capacitive. When the load is inductive, then the current I2 lags behind the voltage V2. When the load is non-inductive, then the current I2 will be in phase with the secondary terminal voltage V2, and when the load is capacitive, then the secondary current I2 will lead the secondary terminal voltage V2. So current I2 will means the magnitude and phase of current I2 with respect to terminal voltage V2 will depend upon the characteristics of the load, whether it is non-inductive, inductive or capacitive. So we start the transformer on load. First we will analyze what happens when the transformer is on no load. So when an alternating voltage is applied to the primary of the transformer, let its voltage be V1, then as the transformer is on no load, then the transformer will draw a no load current I0 which flows in the primary of the transformer. Now if the number of turns of primary is N1, then an MMF will be produced which will be equals to N1 I1. So it is N1 I0, as the current which is flowing right now is I0. Now this MMF will produce a flux phi in the iron core. Now this flux will induce EMF E1 in the primary and EMF E2 in the secondary. Now if the secondary terminal is loaded, then the secondary circuit is completed and a secondary current I2 starts flowing in the secondary winding. Now this I2 is flowing in the secondary winding having number of turns N2, so an MMF will be produced in the secondary winding which will be N2 I2. Now this N2 I2 MMF will produce a flux in the iron core which will be in opposite direction to the original flux. This flux phi 2 will be in opposite direction to the original flux. Means this flux phi 2 will oppose the original flux. And as the flux phi 2 opposes the main flux phi, the main flux phi weakens, due to which the main flux phi reduces, and due to the main flux phi, even, that is the EMF induced in the primary, will also be reduced. So as we know that there is a valence between V1 and E1, which is given by V1 equals to minus E1, it will not be equal as the flux phi weakens. Means the difference between V1 and E1 increases. So in order to maintain this balance, that is V1 equals to minus E1, the transformer draws an additional current which is given by I1 dash. Now this I1 dash is known as the counterbalancing current or the primary additional current, which flows in the primary winding. So another MMF known as N1 I1 dash is produced in the primary winding, which flows another flux phi 1 in the same direction as the original flux or the main flux phi. Now this flux phi 1 will neutralize the flux phi 2, and as the phi 1 neutralizes phi 2, then only original flux phi flows in the transformer core. Means the flux which flows in the transformer core is phi, and again the voltage, primary voltage V1 will be equals to primary induced EMF E1. Now as the flux phi 1 is produced by MMF, N1 I1 dash opposes or neutralizes the flux phi 2 which is produced by MMF N2 I2. So both the MMFs are equal in magnitude and opposite in direction. So from here I1 dash is equals to N2 by N1 into I2. Now the primary current I1 is the sum of I0 plus the counterbalancing current I1 dash. Now as the no load current or exciting current is very much less than the I1 dash, which is counterbalancing current, so we put I1 equals to I1 dash. So we get I1 equals to N2 by N1 into I2, or I1 by I2 equals to N2 by N1, which is equals to K, which is equals to transformation ratio. Hence the primary and secondary currents are inversely proportional to their respective turns, which is equals to